Hey students, so this is the second lesson of section 9.3, and today we're talking about paired data, and we're going to, at the end of the day, we're going to understand why we use a one-sided, a one-sample T procedure to perform significance tests on such data, and understand why and how to use tests wisely. So the first question is, why would we use significance tests for paired data? So that's the main question that's going to drive this lesson. So first of all, we've got to understand what are pairs. So basically pairs are, we have two different things we want to compare. Maybe we're looking at whether or not Ozempic really does help lose weight compared to some other drug. So we want to pair those two data, and we actually want to test whether or not one is doing better than the other. The only difference between one paired significance test and one sample paired data is basically you want to know if the difference between one and another is zero. You want to know if that difference is equal to zero. So basically, you want to know if you got that difference, and the difference being the mean. You want to know if your mean is equal to zero. If it's positive, it tells you one thing. If it's negative, it tells you another thing. If it's equal to zero, it tells you another thing. So in other words, you just want to know whether or not that difference is zero. All right, so here's our first example. And it says this. It says, is the express lane faster? For their second semester project in AP Stats, Libby and Brian decided to investigate which lane was faster in the supermarket, the express lane or the regular lane. To collect their data, they randomly selected 15 times during the week and went to the same store, the same item. However, one of them used the express lane and the other used the regular lane. To decide which lane each of them would use, they flipped a coin. If it was heads, Libby used the express lane and Brian used the regular. If it was tails, it was the opposite scenario. They entered their randomly assigned lanes at the same time, and each recorded the time in seconds it took for them to complete the transaction. Carry out a test to see if there is convincing evidence that the express lane is faster. So this is comparing the times for one student and the other student, and this is what the times are. So basically what we want to know is, you want to know there's a difference between those times by subtracting them and see if that difference is zero. I'm going to use the express lane to subtract the regular lane. So we subtract each one of those. And the difference is -5, -246, positive 46. Well, I'm going to finish this without showing you. So I found all these differences. All right, and this is what we're going to use to actually conduct our test with. But suppose I didn't think to do that. Suppose I just saw these times. I want to figure out if I can make a prediction using just those times. So I just took that sample. And I know nothing about the population, so I only have my sample to go by. Let's actually look at a histogram with just that sample. I'm sorry, box plot. I'm going to put box plot 1 and box plot 2 on the same one. And apparently this is box plot for express lane. This is a box plot for the regular lane. And when looking at that, it's not a big difference, but I do know that express lane does have a shorter maximum than the regular lane, and I know that the regular lane has a higher median than the express lane. So looking at that, it looks like the express lane does have a smaller interval, but this is going to be able to prove it using hypothesis testing. So instead of kind of taking a guess, eyeballing these two, and getting an idea of which one is less, we can actually have definitive evidence. So let's actually go back to our data set. Let's start off with state. So we're going to state what we're going to do. So we're going to state that we will. All right, so here's our statement. We're going to state that we're going to be carrying out a test to see if there's a convincing evidence that the express lane is faster. We'll use the following hypothesis with significant level of alpha equals 0.5 significance. So basically, if I want to know if my hypothesis is that difference is zero, as in these two are the same numbers. So that means there's no difference between the express lane and the regular lane. My alternative hypothesis is that significance level is less than zero. That mean is less than zero. So if that difference is actually less than zero, that means that the express lane is actually faster, because when you subtract them, you get a negative number. Next up, we make it a plan. So is it random? Is it normal? Is it independent? So is it random? They mentioned, and I underlined it earlier, that they were random selected 15 times throughout the day in the supermarket. So the random requirement is there. Is it normal? Because it's less than 15, less than 30, I have to check, see whether or not it's normal. So I can go and actually test that now with my calculator. All right. So if I go to stat and edit, I've already placed these values in list 3. So if I want to actually look at the graph for it, I'm going to go to stat plot, turn it on. I'm using histogram. I'm going to use list 3 by hitting second, the number 3 pops up list 3, then graph. If the graph doesn't show this, hit zoom, and then the number 9 should show this. And that looks pretty normal. I mean, it's pretty approximately normal. I would not say it's skewed at all. That looks pretty approximately normal. So I'm accepting that graph is normal. I'll draw a quick sketch of it. Looking at it, what I'm seeing here. So I'm going to check off that it's normal. And the next thing is whether or not it's independent. So independent decides whether or not that n times p is greater than or equal to 10, or if n times its complement is also greater than or equal to 10. And we had 15 trials, and we don't, in the 15 minutes out of the day, I don't know how long the supermarket is open. We don't really know how long the supermarket is open. It might be a 24-hour supermarket. Who knows? It might be a 12-hour supermarket. So for that reason, we're going to assume that that 15 minutes is less than 10% of the time that the supermarket is open. So we're going to assume that's independent. And then the next thing we'll do is do our calculations. So let's actually calculate. All right, so we're going to go to stat. We're going to calculate one variable statistics. We're going to use list 3 because that's the data we want right now. And it says that the mean is about 42.667. So I'm going to say X bar is about negative 42.667. I'm going to say my sample standard deviation is about 84.02. I think that's all we need to get started from there. And we can actually draw a quick picture of what we're calculating. We're going to assume that our mean, X bar, is equal to 0. And this is at negative 42.67. We want to know the probability of getting the value on that side in this area here. We're doing a one-tailed test, so that's what we're looking for. We don't know anything about the population, so we're going to need to use a t-test. And then the t-test is going to be, well, there's a formula for it we're going to go by. It's basically the mean take away what we expect the population mean to be, divided by the standard deviation over the square root of n. So in this case, that standard deviation of the mean should be 84.02 divided by the square root of 15. So that number is about 21.69. So on the top, we're going to have, well, it's going to be 21.69 on the bottom. On the top, we're going to have negative 42.67, take away 0. And that t-value is about negative 1.9673. Makes sense to me on the left side. So that t-value should be about that. So basically, we want to know that area. We want to know the area related to that t-value. We need a degree of freedom too, though. So that degree of freedom is going to be n take away 1, which is 15, take away 1, which is 14. So I can use a table to estimate that now. All right, so we're looking for negative 1.9673 and degree of freedom of 14. And for that matter, we can be also looking for positive 1.96. So since t-value always has positive values, we're looking for that. So here's my degree of freedom of 14. We're looking for 1.96. So 1.96 is somewhere between these two. It looks like somewhere between 0.5, 0.05, and 0.025. So somewhere in the middle of both of those. So I know that it's going to fail the it's going to fail. The null, we're going to reject the null because it's lower than the significance level. So what we know is that that probability of having a t-value that low is somewhere in between 0.025 and 0.05. Since we can't get it exactly on my calculator, that's enough to prove it. We can stop there and reject the null. But let's go ahead and test my calculator to find that probability. So if I went to second vars, I want to calculate this cumulative t-value. I'm going to use negative infinity to negative 1.967 and degree of freedom 14. Just to be more accurate, that's about 3.4% chance of finding that t-value. So we know p is, instead of using this, I'm going to be even more accurate. I'm going to say p equals to 0.0347. So that value is definitely less than our significant level, which is 0.05. So for that reason, we can make our conclusion now. And here's our conclusion. All right, conclude. We reject the null. And we got to put this back in layman's terms. So instead of saying reject the null, we got to explain it to someone else who doesn't take statistics understands. Since our p-value is less than the significance level of 0.5, we do have enough statistical evidence that the express lane is faster than the regular lane at this grocery store. All right, so that's it. And that's how we actually do that when we have paired data and we need to find the difference between those two pairs. That's all I have. Good luck.